This is Today with Kino Kamis
on Cape Talk.
Welcome to it. It is 25 to 10 and Chris Smith, the naked scientist, with you. Hey, Chris.
Morning.
Hopefully you had a wonderful week, sir. We know that our week ends amazingly well when we have to hear you. Now, here are some of those questions. I see people already calling in. We will be taking those calls. It says here, I have an old-fashioned ice cream maker. It uses, that is cooled using crushed ice and coarse salt. Why is the salt needed?
These old-fashioned ice cream makers are how people back 100 plus years ago, before refrigeration and freezers existed, made ice cream. The way it works, just for those not in the know, is you take a layer of salt, you add some crushed ice, you add some more salt, you add some more crushed ice, you add some more salt, and you make an ice and salt sandwich. Now, if you make a bowl of that and you stick a thermometer in it, the temperature will fall to about minus 20 degrees C. If you have the equivalent amount of ice without the salt in a bowl next door and stick a thermometer in that, the temperature will drift around somewhere between 0 and minus 4. Why the difference? The reason is that when you put salt on ice, the ice is in what we call a dynamic equilibrium with the air around it. There are molecules of water which are constantly trying to leave the ice because by chance the energy which is randomly in the ice occasionally all gets distributed into one little bit of the ice, and one molecule of water has enough energy to break the bonds holding it onto the molecules next door, and it escapes. Now, if it escapes and takes the energy with it away from the ice has lost energy, so it must get cooler. But normally what's happening is that water that was lost comes back and rejoins the ice, so it gives the energy back. So it's in a state of dynamic equilibrium. The temperature doesn't change. If you put salt there, the particles of salt, for want of a better phrase, stop the water molecules that exit finding their way back onto the ice crystal. So it becomes a one-way street. Energy is lost and not given back. So the temperature goes a lot lower. And that's why it gets to about minus 20 degrees C. And you'll end up with liquid water, but at minus 20. And by driving the equilibrium in favour of that lowering of temperature, you get within the regime you need to actually freeze your ice cream and make delicious ice cream.
Fascinating stuff. Now, Paul in Durbanville. Good morning, sir.
Yeah, hi. The force of gravity and the force of magnetism, are they the same or are they similar? And if they are, then can we manufacture a large enough electromagnet on the planet's surface to affect the moon's orbit?
Oh, wow.
Hi, Paul. The answer is that they're different phenomena, and we don't know what gravity is. We have an idea as to how it works, and we know that it's in some way intrinsically bound up with mass. So if you have a massive object, then it distorts Einstein's notion of space-time, the fabric of space, in such a way that things are attracted to you. But exactly why that happens, and the key question also, why is gravity such a weak force? In other words, gravity occurs over enormously long distance, but it falls off very rapidly. It obeys an inverse square law. So if you double the distance, so you go from 1 to 2 meters away from the source of the gravity, then you don't get a halving, you get 1 over 2 squared, which is a quarter of the amount of gravity at double the distance, and so it falls off very rapidly. And we don't understand why gravity works like that, but if gravity wasn't weak like that, the universe wouldn't work. Magnetism is not the same thing. The magnetic force, the electromagnetic force, is quite a different phenomenon. The Earth does have both gravity and a gravitational acceleration towards its centre, and a magnetic effect, because in the centre of the Earth is a pool of molten iron which is moving, and by some technique and phenomenon that we don't properly understand, this creates an effect called a geodynamo, and this molten moving iron, because it's moving charges around, seems to create an effect equivalent to a very large bar magnet inside the Earth, and this creates the field lines which extend out from the poles of the Earth and out into space and fend off the solar wind and other cosmic radiation which would otherwise cook us on the Earth's surface, and we'd all be obliterated. And you can have mass and not have a magnetic effect, because if you look at Mars, for example, Mars has cooled down, lost its magnetic field, but it certainly has a gravitation effect. It's got 2 moons which are faithfully in orbit, Phobos and Deimos, going around Mars. So the two do have the effect of accelerating objects. They do have some similarities, but they are actually completely different entities. Could we make a magnet that would actually be equivalent to being able to fend off the power of the Earth's gravity? No, I think that would actually require so much energy, you'd need a planet-sized source to do it, so I don't think it's feasible.
Well, there we go. Phobos and D-Boss, they sound like two Hollywood rappers. Let's go to Jack in Somerset West. Hello, Jack.
Hi, Chris. Hi, guys. Something that's always puzzled me. We look at stars and we say, all right, those stars are 100 light years away or a million light years away. So what we've seen is like 100 or a million years old. How do we know that they're still there? And obviously they won't be in the same position where they are now, where we see them.
Thanks for that question, Jack.
True on many counts. The stars that we mostly look at are stars which are in our galaxy. That's the Milky Way. The Milky Way is about 100,000 light years across. In other words, if I shone a laser beam from here at one outer edge of the galaxy, it would be seen on the opposite side of the galaxy 100,000 years later. So light travelling at the speed of light takes 100,000 years to get across the galaxy. Distant galaxies, which you can also see in the night sky as smudges. Historically, people referred to these as nebulae because they weren't really sure what they were. It was only later they realised that these distant galaxies themselves are big aggregations of stars. They're much further away. They're millions to billions of light years away. So the universe is truly enormous. When we're looking at this distant starlight, you're quite right, though. Some of those stars, they're not going to be there anymore because the time it has taken the light to get from those distant stars across this vast distance to reach us so we can see it, the star that made that light may not exist anymore by the time the light gets to us. It's also true that everything in the universe is in motion, and in the same way that the Earth is going around the sun is going round our galaxy, and our galaxy is moving as part of a big cluster of galaxies which are also in motion. So everything in the universe is in motion. That's absolutely true. So if you were to wait millions of years and then go to where you thought a star was, it wouldn't be there. That is absolutely true.
Now, another question here. When we were younger, we were told to add salt to boiling water when boiling eggs, as it would make it cook faster. Is this true? Does the salt make the water boil at a higher temperature?
In the same way as we were saying at the beginning of the programme, if I add salt to ice, what does it do? It lowers the melting point. In other words, it makes the water freeze at a lower temperature. Adding any impurity to any other substance also escalates the boiling point. So if you add salt to water, yes, it will boil at a slightly higher temperature. To be honest, though, it's a myth that it will actually affect the temperature at which the water boils to an appreciable amount. It will push it up by a few degrees, probably. I don't think it's more than a few degrees. And that is not going to make really very much difference at all to the cooking time for your food, because relative to the 100 degrees the water's already boiling at, it's going to make virtually no difference to the cooking time. So yes, it will change the boiling point. That's absolutely true. No, it probably is not going to make very much difference at all to how long it takes your pasta or your egg to cook. But it will, if you're cooking pasta, for example, affect the flavour. So salt does have a role. It can affect the flavour of the food, but it probably is not going to be much of a difference to the cooking time.
You're with Cape Talk.
And you're also joined by the naked scientist, Dr. Chris Smith, answering all your questions. And the next question, Chris, is why do lights appear to twinkle from a distance?
The reason for this is because, and I presume we're talking about lights coming through the atmosphere from, say, a distant star. The reason that lights twinkle is because the atmosphere, when light comes through it, changes the speed of the light. Everyone thinks that light has a constant speed, but actually this is not true. Light has a constant speed at the medium that it is travelling through. So a piece of glass, for example, will have light travelling through it at a certain speed. Air will have light travelling through it at a different speed. When light goes from one to the other, it changes that speed, and when the speed changes, it makes the light beam bend a bit. So why should the air have light travelling through it at different speeds? Yep. The reason is that different patches of the atmosphere have different densities. There are masses or patches of warm air and cold air, and this is because thermals are carrying warm air aloft. And so as light comes through the atmosphere, it sees, in inverted commas, bits of the air which are thinner and bits of the air which are thicker. This is directly analogous to the light going from air into glass and back into air again. So as it comes through the atmosphere, the light ray speeds up and slows down many times, and this causes it to wiggle or bend on its course many times. When your eye sees that ray arriving, it presumes that the object that made the ray, because your brain has evolved to think that light comes in straight lines, the object that made it must be moving. So you see apparent movement in the distance from the object that you're seeing that's producing the light, and you assume the star is wiggling around, and that's the twinkling effect that we see.
Well, could that explanation be used for city lights on the horizon, for example, when they shimmer?
It absolutely can. And you can even do this in your kitchen. If you make toast in the morning, turn on the toaster, pop some bread in there so you don't waste the electricity, look at the wall behind the toaster and you'll see a wiggly pattern coming up above the hot vents where the hot air is coming out of the toaster. This is exactly the same phenomenon. The hot air is less dense than the cold air either side of the toaster, so light bouncing off the wall and coming towards you through that air is speeding up and slowing down, wiggling, and you see the wall as wiggling.
Let's listen to yet another question for the Naked Scientist, Dr. Chris Smith.
Hey, this is for the Naked Scientist. I just installed some air conditioners at my house, and I really like to know, how do they work? I really do not understand how it can blow cold air and hot air. And yeah, if I could get an explanation for that, that'd be great. Thanks.
Cold air and hot air. I mean, politicians are very good at that, but air cons, how do they work?
What a brilliant line. The answer to this one is that an aircon is doing exactly the same thing as the fridge in your kitchen and your freezer is doing. Basically, this is the simplest explanation. You take a refrigerant fluid, and there are a whole range of those. You compress them very hard using a pump. When you squeeze a fluid very hard, you're doing work against the fluid. If you do work against something, you're giving it energy. So if you give the fluid energy, its temperature goes up. So the fluid initially gets really hot. You run that hot fluid through a system to get rid of the extra heat, so it chucks the heat away into the room. And then you push the fluid through a very tiny hole so it expands rapidly on the other side of that hole. When a gas expands, it's doing work against the pressure or the atmosphere in the thing it's expanding into. And if it's doing work, it's losing energy. So on the other side of that hole, your expanding fluid plummets in temperature. And the clever thing about a fridge or an aircon unit is that you make the hot side in one place and the cold side in another place. And so you've effectively separated hot and cold. And then by blowing air in the right direction through the unit, you can either collect the heat or you collect the cold, as it were. And so an aircon unit and a fridge are basically electrical pumps that use a lot less energy to pump thermal energy. So you can get heating or cooling to the equivalent of about 3 or 4 kilowatt, and you only need to use about 1 kilowatt of electricity to push that heat backwards and forwards in that way. So in your aircon unit, you push air over the cold element to pull the cold, to basically push the cold air into the room. Or if you reverse the cycle and you use your aircon unit in the wintertime to warm your room up, you're just doing the opposite. You push the air over the hot bit and throw away the cold bit.
Here's an interesting one. Good morning. When I put an earbud in my ear, I get a tickle in my throat, and then I have to cough. Why does this happen? And that's from Colleen in Dip River.
Same thing happens, Colleen, when people put various other things in their ears. There is Arnold's nerve in your ear, and a tiny fraction of the population, 0.9% on, I think, one side, 2.5% on both sides, get this effect that when you ram something into your ear, it produces a cough reflex. And we don't know exactly why this happens, but it's probably a bit of miswiring in the nervous system. But it's called, as I say, Arnold's nerve, and you can stimulate it with objects inserted, such as an earbud or Q-tip to clean an ear. And when you stimulate it, it produces the same reflex that irritation to your throat does to produce a cough. And as I say, you're down in about the 2% of the population who have this.
Interesting question here. Hi, Chris. Can you explain why water dissociates at 42.7 kilohertz? And can this be done at home to extract hydrogen?
I'm not sure I understand the question completely. I think this is something I don't know about, so I'm going to take a rain check, if rain check is the right word to use in a water question, and I will find out what the basis of that is and come back to you next week. Sorry, I can't do that one.
No, not a problem at all. That's the 0.00001%. Now, why does my microwave, when it's on, interfere with my Wi-Fi and my Bluetooth? Asks another question.
The reason for this is that the frequency at which a microwave works is about 2.45 gigahertz. In other words, it's producing 2.45 billion light waves a second. This is the same frequency of microwaves that is used by household Wi-Fi, for example. Now, a microwave oven should be screened so that the metal box, contains and soaks up all the microwaves. There should not be appreciable leakage from your microwave oven into your room. They're supposed to screen the microwaves out. If that is happening, I'd get your microwave checked, because that sounds a bit dodgy to me. But it's possible that your Wi-Fi router signal is a bit weak. In other words, you might have a dead spot where you're trying to receive the signal, and that when you turn your microwave oven on, even a tiny amount of microwave leakage from the oven is enough to overwhelm the signal from the router at that particular position. That could be what it is. But basically, because the two are using the same regime, the same frequency of radiation to send signals, it's a bit like you trying to listen to Cape Talk on headphones and then going to a nightclub. The music that's being played is so loud, using all the same frequencies, that it overwhelms the speech and you can't understand.
And then, the other thing is you could also remove the router out of the microwave.
Yeah, I hadn't thought of that. That's a very good point. I should have said, why are you using your Wi-Fi in your microwave?
And then another one for you, Chris. How do you remagnetize the magnets in a bathroom cabinet door?
Oh, I think I'd just go and buy new magnets, to be honest. Magnets
do
demagnetize with time, because every time you open and close the door, you give the metal a bit of a shock. And when you give the metal a bit of a shock, you can knock off kilter the alignment of all of these little dipoles. Because if you zoomed in with a really powerful microscope on a piece of iron which has been magnetized, you would see that the atoms have what we call a spin state. This is where you can think of this in a very simplified way as the electrons are all whizzing round the atom, all in lockstep, in one direction. And when we magnetize something, instead of the directions all being random through the piece of material, they all line up, all these dipoles line up, and that produces the magnetic field. If you shock a piece of metal or drop a magnet, some of them will be knocked off kilter, and if they're not all pointing in the same direction, they're not contributing to the creation of the magnetic field. So opening and closing the door a lot is going to progressively, because it's producing a little tap to the magnet, it will slowly demagnetize the magnet. Very difficult to remagnetize that in situ to an appreciable degree. I would suggest getting either a new bathroom cabinet or a new magnet.
A lot less effort. And then, Chris, can you please tell us the progress on the possibility of a photon engine for space travel?
I think what they're referring to is that because light has momentum, you can give things a push with light. And there is something called the Yarkovsky-O'Keefe-Radzievsky-Paddock effect, or YORP for short. And this is where, when light falls on, for instance, a large asteroid, it can push the asteroid along. And we have pretty good evidence, for example, that the YORP effect accounted for why asteroids got dislodged from the asteroid belt between Mars and Jupiter, and one of them came and hit the Earth and wiped out the dinosaurs. So we know that light, because it has momentum, when it hits a surface, can give things a push. And people are using solar sail technology, where you put a big reflective surface up in space and you capture a lot of light. And as the photons of light hit it, they deposit their momentum, their energy, and that gives your object to push along. But whether or not you could actually accelerate a spacecraft in this way, I don't think that that's going to work, and we're certainly still in the realms of needing to actually accelerate physical particles. We've got smart engines, ion drive engines, for example, which accelerate electrically charged ions. Xenon as a big heavy ion is usually used, and there was a rocket called Smart 1 that did this, but I don't think anyone's doing it with light yet.
Okay, now this one reads, apologies up front, but why is it that without some form of preview, we don't find our own flatulence to be as offensive as those of others? Does your nose know?
Well, I think there's two aspects to this. One is that we have evolved to be repelled by things that might harm our health, and a really nasty smell could be a signal of things that could infect you with really rotten things and could make you unwell. So you're therefore repelled by those sorts of smells. If you make the smell, automatically you know that you can't infect yourself with something you haven't already got, therefore it's not going to be a threat to you. One other theory I did have is that it could be that because all those nasty smells are already stewing inside you, some of them are going in your bloodstream at low concentration up through your olfactory system anyway, and they're slowly habituating your nose to those smells anyway, so the fart doesn't smell as bad to you as it does to somebody else because you're already used to it a bit.
I'm so glad you said fart and not flatulence. Chris, you must have a wonderful weekend. Great chatting to you. Looking forward to next week. This is, of course, Dr. Chris Smith, the Naked Scientist.